Okay, so you know how AI has gotten just, well, amazing at creating things like images and video.
Absolutely incredible, yeah. The realism is stunning sometimes.
And a lot of that progress comes down to techniques like diffusion models or flow matching, right? They're brilliant for continuous stuff.
Exactly. Things where you can smoothly change from one state to another, like blending pixels or shifting audio frequencies. It's all gradients and smooth transitions.
Right, like sculpting with digital clay. But then you hit this wall when you think about, well, a huge amount of the data we want AI to work with.
You mean things like language?
Language, yeah, or computer code, maybe even biological sequences. It's not continuous at all, it's discrete, made of distinct units, words, tokens, symbols.
Completely different ballgame. You can't just, slightly change the word cat until it becomes dog. It's a jump, a discrete choice.
And applying those smooth, continuous methods directly there, it's been a real challenge.
A major hurdle. Finding effective ways to generate really high-quality discrete data, especially long sequences, is tricky.
Which brings us neatly to what we're diving into today, discrete flow matching. We've been looking at a really interesting paper on this.
Ah, yes. The one on R of if. Discrete flow matching, GAT, and 7 others, I believe. Last updated around November 2024.
That's the one. And it feels like they're proposing something pretty fundamental here, specifically for this discrete problem.
Definitely. A new framework.
So our mission today really is to unpack this. What is discrete flow matching? How does it work, conceptually? And why should we care? Why is it potentially a big deal for AI writing text or code?
Sounds good. If you've ever wondered about the nuts and bolts of how AI generates structured info, this should be right up your alley. We'll try to extract the key bit.
Okay, so let's start where they start. The core problem DFM is designed to solve.
Right. So, as we were saying, flow matching, diffusion, super powerful for continuous stuff, images, audio, video, but getting them to work just as well for high-dimensional discrete data, like long text sequences or complex code, that's been limited.
It's like having a fantastic paintbrush, but needing to build a complex molecule. Wrong tool for the job, maybe.
That's a decent analogy. You need something designed for those distinct building blocks. And that's what they're positioning DFM as, this novel discrete flow paradigm.
Okay, novel paradigm. So what's the essence of it? What are the key new ideas? The abstract points to a few main contributions.
One of the first big things is flexibility. It's designed to work with a general family of probability paths.
Probability paths. Okay, what does that mean in practice?
It means instead of having just one fixed way to get from, say, random noise to your target data, like a specific sentence, DFM allows for many different possible routes or ways to interpolate between the start and end points in this discrete space.
Ah, so it's not just one highway from A to B. It's like having a whole map of potential roads.
Exactly. Some might be more direct, some might go through different intermediate stages. This gives the model more flexibility to learn the best way to transform noise into something coherent, like text or code.
Okay, more learning flexibility. What else?
Tied to that is the second point. They provide a generic formula for sampling from these paths. This is the how-to part. How does the model actually use these paths to generate new data points?
Right, the practical mechanism.
Yeah.
And the paper mentions using learned posteriors and things like six-stocks prediction and epsilon prediction. Can you demystify that a bit?
Sure. Let's put the jargon aside for a moment. Imagine the model is somewhere along one of these paths looking at a sort of partially formed or noisy piece of data.
Or like a garbled sentence fragment.
Yeah, exactly. A learned posterior just means the model has learned, based on seeing lots of examples, how to figure out what the original clean version of that garbled bit should probably be.
It learns to denoise or complete it, basically.
Precisely. Now, how it figures that out can vary. The generic formula allows for different strategies. Six-star prediction, where usually stands for the clean data, is like the model trying to directly guess the entire final clean output based on the garbled input it sees.
Just jump straight to the answer.
Kind of, yeah. Whereas epsilon prediction, where epsilon often represents the noise or the error, is more like the model trying to figure out what specifically is wrong with the current garbled version. What's the noise? What's the error?
So it identifies the mess.
Right. It predicts the mess itself, so then you can effectively subtract or remove that mess to get back to the clean version. The key point is that DFM provides a unified way to sample effectively using either of these learned strategies, or potentially others too.
Got it. So it learns to clean up the data, either by guessing the clean version directly or by figuring out what the corruption is. And the framework supports both approaches. That makes sense. And this links to their third point about performance.
It does, yeah. Because they have this flexibility in paths and sampling, they show that by carefully choosing which paths to use defined by different schedulers, basically different ways of adding noise or moving along the path they achieve, improve generative perplexity.
Perplexity, that's a common metric, especially for language models. Lower is better, right? It means the model is less surprised by the real data.
It's exactly. Lower perplexity generally indicates the model is doing a better job of predicting the sequence, which usually translates to higher quality, more coherent generated output. So better perplexity than previous discrete diffusion or flow methods is a good sign.
And this wasn't just a toy experiment, they scaled it up.
That's crucial. Yes, they tested models up to 1.7 billion parameters, which is, substantial. And they tested on some pretty challenging tasks, particularly code generation.
Ah, the coding benchmarks. Human Eval and MBPP. These involve generating actual Python code to solve programming problems.
Yep, really non-trivial tests. And the results they reported are quite noteworthy for a non-autoregressive approach like this.
What were the numbers again?
On Human Eval, they got 6.7% pass at 1 and 13.4% pass at 10. And for one-shot MBPP, it was 6.7% pass at 1 and 20.6% pass at 10.
Okay, and pass 1 means the very first code it generates works. Pass at 10 means it gets it right within the first 10 tries.
That's right. So getting these kinds of numbers on complex coding tasks demonstrates that this DFM approach isn't just a theoretical curiosity. It has practical legs.
So summing up so far, a new method for discrete data, flexible learning paths, smart sampling that learns to clean up data, better quality metrics like perplexity, scales well, and gets solid results on hard coding problems. Wow. What's the biggest conceptual leap here, though?
I think the most significant takeaway they emphasize is that DFM achieves this level of quality while being non-autoregressive.
Non-autoregressive. Okay, let's unpack that, because most big language models we hear about are autoregressive, right? They generate text token by token, one after another sequentially.
Correct, like typing out a sentence word by word. Non-autoregressive models, on the other hand, have the potential to generate parts of the sequence, or even the whole sequence, more. Well, in parallel or in a different order.
Routes once, potentially.
Potentially. Or at least in larger chunks simultaneously. And the paper makes a strong claim here. They say DFM significantly closes the gap in performance between these non-autoregressive discrete flow models and the dominant autoregressive models.
That feels huge. Why is closing that gap so important? What's the big deal about non-autoregressive generation if autoregressive already works so well?
Well, there are a few potential advantages. Speed is a big one. If you can generate parts in parallel, you can potentially generate the whole sequence much, much faster than going token by token.
Latency, okay. Makes sense.
Yeah, and sometimes non-autoregressive models might have different desirable properties. Maybe they're less prone to certain kinds of repetitive errors, or maybe they're better suited for tasks that involve editing or infilling, where you want to change multiple parts at once.
So it opens up different possibilities.
Exactly. Autoregressive models have kind of set the gold standard for quality, especially in language. Showing that a non-autoregressive method like DFM can get genuinely competitive and significantly narrow that quality gap is a really big deal. It suggests we might not have to rely solely on slow, sequential generation for top-tier results in discrete data.
It unlocks a different way to think about building these models.
Precisely. It's proof that alternative approaches can be powerful and practical, which could spur development of faster or more flexible generative models for text, code, and maybe other discrete domains too.
Okay, so wrapping this up. Discrete flow matching looks like a really promising new direction. It's specifically built for discrete data like text and code, uses these flexible learning paths, has clever ways to generate data by learning to denoise it, and shows improved quality.
And importantly, it scales up and performs well on tough tasks like code generation.
Right. And the big headline is that it does this non-autoregressively, really narrowing that performance gap compared to the standard token-by-token models.
Yeah, it's a significant step in developing new tools for generating structured information, which is just fundamental for so much of AI.
It really makes you think, if a non-autoregressive method can achieve this level of success on something as structured and, frankly, complex as generating working code, what else could it be applied to?
Good question.
Could this kind of approach, generating things more holistically or in parallel, fundamentally shift how we build and maybe even how we use generative AI for language and code down the line? Something to chew on.